Before we start, some of the key things about functions and understanding and remembering what functions are. So functions is a set of rules that applies to some inputs to result in a singular output. So it has to result in a singular output. So often we've kind of shown mapping diagrams indicating functions. So suppose we had the function f, an input given a singular output, that would be a function. You could have another input going to that same output, but still that input is producing a singular output. So still it is defined as a function. So the definition of a function is an input results in a singular output. So although it's the same output from both inputs, each input in its own right is resulting in a singular output. If we have the case where an input results in two outputs, that is not a singular output, this would then not then be defined as a function. So make sure you know what the definition of a function is, because often you might be asked that for a 1 marker. So that's some of the basis of functions. You could have a function one applied after another, and that's essentially what composite functions are. So a composite functions is essentially you'll have a function applied. So suppose you have f applied first, and then you might have g applied next. This is what happens. The input of this goes to the output here, and then this output results in this output then becomes the input of g, which results in the final output. So what function is applied here first? F. So it's f is applied to the input of x, and then that f of x, this output then becomes the input to the function g, which may be written like this: g with f of x inside a bracket, indicating that this is the input to g and x is the input to f, which is why it's written in that way. So that's a kind of explanation as to why we write g first, because actually you're applying x into f followed by f of x into g. And the details of this, so I did go through when we went through functions during lockdown, and you should have a video more detail about that. But this is just a little overview, kind of some of the key important things about functions before we look at this question. So that's the second point. So we talked about function, we talked about composite functions. Inverse functions, what they are is a way of going back. So I'm trying to give you visual representations of all of these things. So suppose we have the function f applied here from that input to that output. If you want to go from that same output to that same input, there must be a particular way of doing that, and the function is defined as f minus 1, or the inverse function of f. And it will be a case of applying the inverse operations. Now, an inverse function also exists only for a one-to-one function. So a single input given a single output, then from that single output, we can go back to that single input. So that's an inverse function. The process of finding the inverse function you should know, and then you should understand why certain things, certain steps that we take during the inverse function when we swap the y and the x. And that's essentially because if you think about it, the input of the inverse function is the output of the original function, because we're going backwards. And so that's why we swap the x and the y value, because for the inverse function, its input is the y value, but we actually write it in terms of x notation, which is why we swap the y and the x. So that's a little brief overview, a visual representation about inverse functions. We talked about composite functions. And with inverse functions, since the x and y coordinates swap, that essentially means that the domain and range of an inverse function is essentially the reverse of the original function. So the domain and range swap, again, for that particular same reason, because the inputs and outputs swap. So that's really important to remember, because often it's a 1 marker and it asks you to find the range of the inverse function, but you already have the domain of the original function. So it's just a case of, do you know how to find it? And just stating that for a 1 mark. So that's kind of some important things about the inverse functions. And the other thing which I would also mention is when you're asked to find the domain and range of any particular function, a graph is a really important part of understanding what the range is for a given domain. So drawing where possible. If the function is a bit complex to draw, you could use a table of values using your calculator to then draw a sketch as to what it might look like to actually try and understand what the range will be. Okay, so we'll look at that kind of what I mentioned about domain range in this first question, and I think that's going to be the focus of the functions topic. So let's go and take a look at this first question. Just put this to a side. So here's our first question. It says here the function f and g satisfy the below. So we can see f of x is given by an exponential function, g of x is ln. So it wants us to find out what f g of x is in its simplest form. So this is essentially saying, okay, let's find out it's input x inputted into g, and then the output of g becomes the input of f. So algebraically, I mean, that should be relatively straightforward to do. We're looking at where f of x is, and if we start off with f of x, instead of x, I'm going to be inputting g of x into f of x. So wherever I saw x in my f of x, I'm going to replace it all with the function g of x. So it becomes 2e to the power of half, and the x becomes my g of x, which is ln of 4x. Okay, so that's what we've got here, f(g) of x. Now we can't leave it in this way because it's asked for us to write it in its simplest form. So we need to go and manipulate this. So this is where you need to use some of your laws of exponentials, laws of logarithms, and so on to tidy this up a bit. So what can we do here? Well, let's first of all look at the fact that we've got an e and an ln, and we know they are the inverse of each other. So there could be a case where when you do the inverse of something, it results in you getting back to the same place, i.e. equaling 1. But in order to get there, we need to get to a state where there is no coefficient in front of ln. It should be e to the power of ln of something. But so we're going to have to deal with this half first. There's a half in front of this ln. So I know I did put a bracket here, but if we did times it by that half, the bracket would go away. So it would be half ln 4x. And then applying the power law. Now notice here, there is no bracket after ln. But you need to understand something here. When we have ln of something written like this 4x, it's actually indicating that it's ln of 4x. Okay, it's not ln of 4 times x. Otherwise, there would be something clearly kind of like that would have been distinguished, differentiated in some way. So if something is written like that, there is a bracket there. So I'll put the bracket in just so we understand that there is a bracket in here. There's a bracket. There's a bracket. So what am I doing with that half? I'm putting it as a power on this 4x using my log law, my power law. What else can I do now? Well, now that I've got it into this stage here, e of ln of 4x to the half, I can tidy this up now. So now that I've got no coefficient in front of that, I can do e of ln, which is essentially the inverse of each other. So that kind of cancels. So you've got 2 lots of 4x to the power of half. Okay, I could have done the half on the 4x, but I've just left it there and I'll tidy it up now. So tidying this up, we've got here 2 times 4x to the power of half, so 4 to the power of half, and x to the power of half is essentially what that becomes, because the half is on both the 4 as well as the x, and then all multiplied by 2. 4 to the half is essentially square rooting of 4, which is 2. So you've got 2 times 2, which is 4. And x to the power of half is the same as root of x. So you end up with 4 root of x. And so that's the as simplified as you can leave it in. You can leave it in that third form, 4 root x. So that's the first part. And then it goes on to ask you to find the domain and range of f(g) of x. Now, this bit is the kind of the really important bit. The whole point of why I'm going through this is to understand domain and range a lot, because that's where a lot of the mistakes happen. That's the bit that students find most difficult, in my opinion, from experience with functions. Not to do with finding composite functions, inverse functions, people are okay with that. It's when you're trying to state the domain and range. So how do we find the domain and range of fg of x? Well, let's understand what's happening here, fg of x. Fg of x is this case here. You've got the function g being applied first, which gives a certain input will give a certain output. And then that output of g of x then becomes the input to the function f. And this is our function f g of x. Okay, so we need to look at what is the domain first of all of g, because g is essentially what's been applied first. Now they've told us what the domain is for g. G is all real numbers, but also x is greater than 4. So that's the domain we're going to start off for the composite function. But that might not necessarily be the domain of the composite function. We need to consider if there are certain values of x for which this function is not valid, because it might not be x is all greater than 4. There might be some other things coming into it. So we need to consider all of that. Okay, so let's just take a look. So we were saying here the domain here is x is greater than a quarter, and x is a set of all the real numbers. And so that gives us an output. Well, let's take a look at what output we get for this particular range for x is greater than a quarter. Well, we need to look at our g function. Okay, our g function is an ln function, and we can see here that for the ln function, so long as x is greater than a quarter, so I'll just write down my g function here, g is equal to 4x. What does the ln curve look like? You should be able to sketch that, and so sketching is really important, and understanding what's happening with your curve enables you to find out what's happening with the range. So what does the ln look like? Well, we know what the exponential ln is essentially an inverse of the exponential function. Ln looks something like this. Okay, ln curve, and we're looking at the case where x, we've got 4x here, so there's a value of 4 there. What does that do in terms of transformations? What that does is it divides all the x values by 4, if you think about translation. So if it divides all the x values by 4, normally it would have went through x is equal to 1 here, so then this would become a quarter. Okay, you would have an asymptote at x equals to 0. If you divide that by 4, that doesn't change. So your ln 4x graph looks something like this. And we're saying that when x is greater than a quarter, well, when x is greater than a quarter, what can we see is the range. So this is where range is easy to see. Rather than trying to look at it algebraically, range refers to all our y values, our outputs of ln of 4x, all the y values. So when x is greater than a quarter, we're looking at this section here. I'll just highlight that, this section here, and it goes on. For that section, what are my y values? Well, x is greater than a quarter for that section. Look at my y values. They are all greater than 0. So essentially, what do we have then? We're then saying the output of g of x is where x is, output is always greater than 0. I'll just write down here, g of x is greater than 0, i.e. the output of ln of 4x is 0, greater than 0. So then this now becomes my domain of the f function. So that's how we look at composite functions. So this has now become my domain of the f function. Notice here though, the domain of the f function given originally on the single function f of x is all real numbers. But here, the domain, because we're looking at a composite function, we're looking at inputs of g of x, which gave certain outputs, and the domain of g of x limited the output of g of x to being greater than 0, as we can see here, as we kind of use that domain to get this output. Therefore, the input of f of x, the domain of f of x now becomes everything greater than 0. So for that, we can actually then go and look at what that will do to the f function. I'll write down the f function. F of x is equal to 2e to the half x. And again, we can sketch that to see what that would look like. Here's a sketch. What does the exponential function look like? Well, that's what it looks like. What does that half do? Well, half multiplies all the x values by 2. That value was a y value. So when it multiplies all the x value, it doesn't actually do anything to the shape for this one because there's no intercepts. So it would still look like that. What does that 2 do? It multiplies all the y values. Now we had an asymptote at y equals 0. Multiplying that by 2 doesn't have any effect, so that remains at y equals 0. We would have had an intercept at 0, 1 here, but multiplying by 2, that affects that y value. That becomes 2 now. So this is the function 2e to the half x. What is its input? Its input, well, look at here, are all values of g of x greater than 0, i.e. its input, its domain is x is greater than 0. Because remember, its input is the output of the g of x. So for x greater than 0, which part of this function are we looking at? X greater than 0 for this one, we're looking at this bit here. So for that bit, what are my y values? My y values are everything here, i.e. everything greater than 2. So what does that do to my, what does that mean for my range of this composite function? Well, for that input, I got this output for g of x, which became the input of f of x, which then meant my output for here, f of x, or fg of x, I should say, will be everything greater than 2, its range. So I found my range for fg of x by using this diagram to show which functions implied which input gave us which output, and then that output becoming the input of my next function, the f. I looked at it using a graph as well to understand what the range is. Okay, so now I know my range. What is my domain? Well, let's go with that original domain. X is real numbers, x is less than greater than a quarter. Are there any values within there which will kind of result in this function not working, the f of x function? We know it works for g of x, but is there any values greater than a quarter which we can say doesn't work with 2e to the half x? No, because all values will give appropriate answers. So what is the domain for this? Well, the domain is x is all real numbers, x is greater than a quarter. So what's our answer for this? The domain in the range, this is the domain. And this is valid for both g of x and f of x. And what's the range? This is my range. Fg of x is greater than 2. Okay, so this finding domain and range, as I said earlier, is the thing that students find most challenging with functions. And my solution to that is draw a diagram, a flowchart for composite functions. Draw graphs for each function to understand what range. Highlight the part of the graph for your given domain, and then highlight the range for that given domain and work with it in that way. Don't try and do it algebraically, because then you don't have that visual representation in your head. Algebraically, it's hard what range is going to be and what domain is going to be. Okay, so that was part B of that question. And then it goes on to say part C, which is the solve. What's this? Fg of x is equal to 3x plus 1. Okay, so Fg of x is equal to 3x plus 1. So that's just a straightforward case of going in, and we can look at this both algebraically as well as graphically. Graphically, what it means is if we had the Fg of x function drawn, where would it intercept with the function 3x plus 1? So we've got a linear graph and Fg of x function, both on the same thing. Now we already found out what Fg of x is. Fg of x is 4 root x. It's this function here. So if we did draw that and the linear one, where would they intersect is essentially what we're looking for graphically. But we can solve this algebraically here, probably easier. So there's Fg of x is equal to 3x plus 1. So what is Fg of x? Well, we found that out earlier. It's 4 root x is equal to 3x plus 1. Okay, so go ahead and we're going to solve this now. So I'm going to start by You can do anything here. I'm going to start by squaring both sides because I've got this root which looks a bit messy. I can see here what this is likely to be. I mean, you can probably see, if I write this as a power, it might help you see it a bit easier. Always equate things to 0. I would always do that with all equations when we're trying to solve. So you essentially end up with 3x minus 4x to the power of a half plus 1 equaling to 0. Now, the x has a power of 1. There's something to spot here. Whenever you have two terms such as x to the power of 1 and x to the power of half, if the power on one is double the other one, that is a way of recognizing hidden quadratics. Okay, that's a way of recognizing hidden quadratics. If one is double of the other, so you would say let x to the power of half equal to, introduce a different letter here, so maybe y, and then you will get 0 is equal to 3y squared minus 4y plus 1. So you've got a hidden quadratic. Okay, so then you would go ahead and solve this, and solving this would get us, let's see, 3 times 1, 3. Let's see what we can do here. 4x, 3x plus 1, yeah. So yeah, so if I mean, you can go and use your calculator here to actually find the solutions of this. You are not in the exam assessed to see whether you can use the quadratic formula and things like that. So once you get to this stage, you can use that function in your calculator, the equation function, and put in polynomial degree order 2 and put in a, b, and c as appropriate to actually find out what those values are. And I think the values that you get here, let me just get my calculator out. I'll actually probably go and let me see if I can do 3 times 1 is 3. We'll do it differently. I'll do it by factorizing. So I'm going to look for the factors of 3, minus 3 and minus 1. So I'll factorize it using the AC method. 3y squared minus 3y minus 1y plus 1. So then I end up with 3y, y minus 1, and then I've got y minus 1 here as well, minus 1. So I've got 3y minus 1 and y minus 1. So that means y is equal to a third and y is equal to 1. But then go and find values of x, because y was something that we introduced. So y is x to the power of a half is equal to a third, and x to the power of half is equal to 1. So how do we find out what x is? Well, if you've got power of half, we need to do the inverse of that, which is square both sides. So x is equal to 1 over 9, and squaring this gets us x is equal to 1. Now be careful here. Don't just leave it like that. Actually check, are these results valid for the question that we're trying to solve? Are both of them valid? Well, go and look at what we had originally. What did it say? Look at the domain of the function that we're solving. Okay, x must be greater than a quarter. And what did we have here? We've got two values where one is x is equal to a 9. That is definitely not greater than a quarter. Okay, x must be greater than a quarter was our domain, and x is a set of all the real numbers. So this does not work. So the value that would go with it here is x is equal to 1. Okay. How do we know this doesn't work? Well, what is that we're actually solving? Remember what I said earlier? Fg of x is equal to 3 of x plus 1 means if we were to draw Fg of x, okay, and if we were to draw 3x plus 1, where would they intersect? But Fg of x is only drawn for values where x is greater than a quarter. So surely it's got no curve drawn for less than a quarter, i.e. for x equals to 1 over 9. So therefore there won't be any intersection with 1 over 9. Okay, so this is where the graphical understanding will help you to figure out why x equals 1 over 9 doesn't exist, because the curve doesn't exist for x equals 1 over 9. Fg of x doesn't exist for that part. Okay, so any questions about that? Okay, so should have well, pretty much finished most parts here. Maybe even the solving part shouldn't have been that difficult. Is there anything you want me to go through from this? If you don't have anything to go through, I'd like to get on to the next part. I think finding the range of f of x, I mean, if you draw a sketch, you should be able to see that quite. The answers are at the bottom, as you can see. It says here f of x is less than or equal to 3. So if you were to draw the sketch, you would see that the y values does not exceed 3. It's always less than that. It's a parabola upside down negative. Then it goes on to say find the inverse function. So that's just a case of so the process of finding the inverse function, just applying that and further stating its range. Now we know the inverse function of the range of the inverse function is the domain of g of x. So the range of g minus 1 of x will be the domain of g of x, and the domain of g of x is all real and x is not equal to minus 1. Therefore, the range of the inverse is not equal to minus 1. Should have been straightforward. Determine the composite function. That should have been okay. Don't think anyone should have had any issues with that. Find f of x and then substitute it into g of x. Okay. And if anything, I think the bit that might prove a bit difficult is part D, which is find the domain of g of x. Part E is just a straightforward, again, solve question, but then you need to see if both solutions are valid by comparing it to the domain of g of x. So part E is somewhat related to part D. So if anything, I'll just maybe just kind of briefly highlight on this bit here, the gf of x. What is the domain of g of x? Now, you've already found gf of x. Gf of x is equal to 2 over 4 minus x squared. How is this made? Well, it's made from applying fx first and then g. What is the function f? It's 3 minus x squared. And what's the function g? It's 2 over x plus 1. It starts off by saying that g is, f is has a domain of all real numbers. So for all of those real numbers, we can get anything here. We know f of x will have outputs which are less than or equal to 3. Okay, and that was something we had to find out. So then we're saying here that the x value, the input of g of x will be everything that is less than or equal to 3. Will everything less than or equal to 3 work for this? Well, look at g of x function. You can see that it's a reciprocal function here, 2 over x plus 1. X, we know the denominator, if it's 0, it's undefined. So what would make this denominator 0 is if x is minus 1 here. Now for x to be minus 1, so we're saying here that here we have minus x. Now how if minus 1 is an output of f of x, what x value will result in the output of f of x? Oops, the output of f of x being minus 1. What input value here will result in the output being minus 1? Well, take a look at that function here. You can just say 3 minus x squared equals minus 1 and find it that way. We can see it quite clearly by just figuring out. The only way we'll get minus 1 here is if this x squared value is 4. Okay, how can we get x squared value to be 4? Well, x squared value could be 4 if x is equal to either minus 2 or plus 2, because minus 2 squared or plus 2 squared will result in it being 4. 3 minus 4 results in this output being minus 1. Is there an algebraic way of solving that? Yes, you could have just said 3 minus x squared is equal to minus 1, the output, and then rearranging and solving. Same thing. Okay, so I just did it in my head by looking at it. So a value of plus or minus 2 would result in an output of minus 1, which is a value that does not work with the g of x function because it's undefined. So this is something that won't work. So the domain of the composite function gf of x is not all real numbers, as we can see here. So don't just assume it's always going to be whatever the domain of the first function applied is. It's not. You have to consider, is it going to work for both of them? And as we saw here, there was one particular value of x that doesn't work for the g of x function, and that value we saw was a value of minus 1 here, which meant that the original input had to be plus or minus 2. That doesn't work. So what is the domain of the composite function g of f of x? Well, it's everything as long as it's not, as long as x is not equal to plus or minus 2. Okay, so x can be anything so long as it's not plus or minus 2. And that's how we get that domain. And that required us to really understand this diagram and really think about what the inputs is, what the output is to each function. Okay,